Alright, so pretty sorry for the break in transmission. I just had to make sure that our live chat is on. So that you can easily drop your questions. I observed that I did not activate live chat, so I had to quickly start up a new live. Alright, so if you are currently on this call, you're currently on this class rather, please do well to indicate. Let's do a thumbs up, please. If you are in the chat, do a thumbs up and drop a message in the live chat before we start. If you are in the call, do a thumbs up and drop a message in the live chat. Let's begin. I'm waiting for you. Let's go. Do a thumbs up and drop a message in the chat. Do a thumbs up and drop a message. I see you, Wumi. Active, full granular. All right, please, if you are in the call, drop a thumbs up and drop a message in the chat. Drop a thumbs up and drop a message in the chat even as we begin. Drop a message in the chat and do a thumbs up. We have 3 persons in the class currently. Where are the others? We have 3 persons now in the chat. Please, if you are online, if you are in this call, drop a thumbs up. Or drop a message in the chat to show that you are on this call, you're on this, or rather in this class. Let's go. If you're in the call, okay. Let's do a thumbs up to this class. Drop a thumbs up if you're in the class. We're about starting. Remember what we're talking about today? We're talking about change of state and latent heat. So let's get our notepads, let's get our pen and our calculators ready. Remember, once again, it's physics clinic. And today we are looking at change of state and latent heat. So please, let me see those thumbs up. We are about starting. Drop a like if you're on the call. If you're in the chat, drop a like. We'll be starting soon. We'll be talking about change of state and latent heat. While we wait for others to join up, I'm just waiting for us to get up to like 10 viewers. We'll kickstart as soon as possible. Just drop a thumbs up if you're in the call. Welcome to yet another moment, another time. Physics with Polami. Here's our weekly series, Physics Clinic. live here on YouTube on this channel. For the past 2 weeks, we'll be talking about heat measurement. We have seen what heat and temperature is all about, how it can be measured in real time. We explored specific heat capacity as well as heat capacity and the calculations that is involved. We used certain exams as case studies, the West African Examination Council exams, the Joint Admission and Matriculation Board, JAMB UTME, as a case study, and we saw standard questions in these exams. Last week, we rounded up calculations under heat capacity and specific heat capacity, and today we are going to be looking at change of states and latent heat. Change of states and latent heat. All right, so we'll be starting ASAP, as soon as possible. All right, so I have 4 persons currently in the class. So I want these 4 persons to quickly drop a like on this call. It's thumbs up. Let's punch the like button even as we proceed. The like button even as we proceed. We are starting now. We have 4 persons in class already. Let's just drop a like and we proceed. Now. All right. You're welcome to class this beautiful Sunday afternoon. It's my pleasure to welcome you. My name is Paul. They call me Paul with the vitamin, and we're still on our series Physics with Paulamine, where we talk about basically on our series Physics Clinic, where we take our time to explain certain physics concepts that students usually see as difficult, that students usually see as challenging. All right, so we are going to be addressing these topics in this our life section, step by step, in the simplest form and simplest explanation possible. We are going to be explaining this physics concept. Okay, so like I mentioned earlier, for the past weeks we have been dealing with heat measurement, how heat can be measured, how bodies are receptive to heat, conduction of heat and all, and what specific heat capacity is all about, and the various calculations under it, especially when we are considering certain exams, especially in Nigeria and in West African Examination Council exams, the Nigeria Examination Council, NECO JAMB, UTME, Post UTME. These are topics that if students pay attention to, if students they comprehend and you understand, it will be easier for them to ace these exams. All right, so that's why this physics clinic is holding to explain these physics concepts in details, in the most clearest form and in the most clearest format. All right, so if you are in this call, I can assure you that you are in for value today, you are in for value tonight, you are in for value in this particular section. All right, so do not go anywhere. We are about starting. All right. Okay, so I'm just trying to check that we have everything in place before we commence. Just trying to check that we have everything in place before we commence. All right, so okay, let's see. Okay. hand. Are we good to go? Are we good to go? If you are ready for me this evening, let me see your comments. Just say go, sir. If you are ready for me, indicate in the comments, indicate in the live chats, go. Just send in go. Comment the word go in capital letters, G-O, go. Let us commence this class as soon as possible, right about now. All right, I've seen 2 goes. Go, sir. All right, we're proceeding in anytime soon. All right, let me get one more go and this class commences. I want to believe we can see the board clearly. How is the visual from your hand? Is it that clear? If it's not, let me know also. How is the visual from your hand? How is the visual from your hand? Can you see the board? Is it visible in your hand? If it is not, please do well to let me know. I just want to make sure that we have everything in place before we commence. We have spent so much time already. Just trying to ensure that all technical issues is put under control. All right, so we commence right about now. All right, so I'm sorry for that once again. I was just trying to check connection. It was a bit off. All right, so let's quickly commence. We're talking about, like I mentioned, looking at change of states. We're looking at change of states where we're going to be considering latent heat. Change of states, we're going to be considering latent heat. Alright, so I'm going to proceed by simply talking about alright, please just give me some minutes, please. Okay, so sorry about that. So I'm going to proceed by first of all listing out the effects of heat. All right, when heat is added to a body, when heat is added to a particular substance, there are certain effects heat will have on that body. There are certain results that we will likely see happen to such bodies when heat is applied to them. All right, we have one of them is change in temperature. When heat is added to a body, we usually experience a change in temperature of such body. There's always a change in the temperature of such bodies. Then secondly, when heat is applied to a body, we usually experience chemical change in that body. Chemical change of that body. For example, when we consider the burning of wood, wood, chemical change results. Okay, when when it is added to wood, it burns the wood, and that's an example of chemical change. The application of heat resulting in chemical change. We also have physical change. One of the effects, the third effect of heat. When it is added to a body, it results in the physical change of that body. Example, when we consider which substance is that again now? When we consider iron, when we heat iron, it becomes red hot, like it practically changes its physical form. It becomes red hot. There is a change in its physical appearance. That's one of the applications of it. Another one is the change of state. That is to say, when it is added to a body, it causes the body or the substance to change from one state to the other. All right, so change from one state to the other. For example, we are told that we have several forms matter can exist. Okay, we have the major ones, the 3 major ones, which is solid, liquid, and gas. All right, the three major states or major forms of matter. Okay, so when it is added to, let's say for example, a substance in its solid state, that substance tends to change its solid form to either liquid or maybe what, gas. All right, and that only takes place when heat is added to such a body. All right, so change of state is one of the effect of heat on a body. Then if we consider the fifth one, we have thermionic emission, we have thermal expansion, we have several others. We have several others. But today we are going to reduce or break down our scope or horizon to just change of states. The effect of heat resulting in what? In change of state of a substance. The change of state of a substance, all right, which is as a result of what? Of it. All right. So if I'm to ask, what is a change? What is change of state of a body, or basically what is change of state? All right. Now, change of states is simply a process. Yes, it's actually a process. All right. It's simply a process where a substance changes from one state to the other due to the application of heat. All right. Okay, it's the what? Change of a substance from one form or state to the other due to application of heat without, yes, where the most important, this is the most important part of the definition for change of state. All right, without a change in its temperature. All right, so a substance changes from one form to another. A substance changing from one form to another when heat is applied. When heat is applied without causing a change in its temperature. All right, so we establish the fact that when I have a solid material, changing to liquid, the process where this solid material changes to liquid, okay, is change of state. All right, it's changing from solid to what? To liquid. And from solid to liquid, we are told that the temperature of the body does not change. The temperature of the body remains constant, remains the same throughout the process. That's why we see, for example, water. Okay, ice water in its solid state, ice. All right, when ice wants to melt, the process where ice turns from ice basically to liquid, to completely being liquid, that process takes place at a constant temperature. That is, the temperature does not change. Okay, that's why melting of ice takes place at 0 degrees Celsius. At this temperature, there is no observable or noticeable change in temperature. The temperature remains at 0 degrees Celsius for as long as the ice is still changing into liquid water. For as long as the ice is still changing into liquid water, the temperature remains 0 degrees Celsius. All right, so change of state always takes place at a constant temperature until the substance has completely transformed into its new state before there is a change in temperature. But for as far as the process of change of state is still ongoing, there is no noticeable or significant increase in temperature. All right, so that is the idea about change of states. A substance from one form to another, whether from the solid form changing to liquid, which is called melting, or fusion. Solid changing to liquid, which is called what? Melting or fusion. Or the substance is already in its liquid form, changing into its gaseous form. All right. For example, if we consider water, okay, water changing into vapor, liquid water changing into vapor is called vaporization. All right, it's called vaporization, the process through which a liquid substance or a substance in its liquid form or in its liquid state changes into vapor at a constant temperature. All right, so the constant temperature for which a substance changes from liquid to vapor is what we all know as boiling. Is what we all know as what? As boiling. All right, so boiling is a process where a substance changes from its liquid state to its gaseous state at a constant, fixed, definite temperature. Alright, it is at that temperature that boiling what takes place, and it is constant. It means that when a substance is changing from liquid to vapor, alright, that liquid will remain at 100 degrees Celsius until all the liquid has been changed, the liquid in that vessel has been changed into vapor before there will be increase in temperature. Okay, but for as far as the process is still ongoing, the temperature will remain the same. For example, if I'm considering water, right, the vaporization of water takes place at 100 degrees Celsius. Alright, this temperature will remain this way until the vapor contained, or the liquid molecule contained in that vessel, they have all been transformed into vapor. They have all been transformed into the gaseous state before there will be any observable increase in temperature. So that's the idea of change of states. Solid to liquid, we call it melting or fusion. Then liquid to gas, we call it vaporization. Okay. Now, this is when heat is added. All right. So it means that in the reverse, if I could consider the opposite direction, if it is removed from a vapor, all right, from steam, that steam will carry out a process called condensation. All right, the steam will condense back to liquid. It means it will change its form back from being in its gaseous form back into its liquid form. That process is called condensation. All right, the more heat we now remove, the more heat that is removed from such a system, or if it is removed from that liquid water, okay, that liquid water is now transformed, or it changes state again into the ice state, or the solid what? The solid state, in a process called freezing. Alright, freezing. In some other materials aside water, we say a process called solidification. Alright, but when we consider water and some other types of liquids, we say that freezing takes place. Alright, so if I remove it from a liquid substance, or a substance in its liquid state, such a liquid becomes a solid by freezing. Alright, by freezing. So that's the process. So if I'm adding it, it moves from solid to liquid. The process is called melting or fusion. Alright, if I'm moving from liquid to gas, the process is called vaporization. Sorry, I'm crowding the board. Alright, the process is called what? Vaporization. Now, if I take it backwards, if I reverse the situation from gas back to liquid, is a process called condensation. From gas back to liquid is a process called condensation. Alright, and now if I'm in the liquid state and I want to take it back to the solid state, is a process I call freezing, or generally we'll say solidification. Solidification. Generally we say what? Solidification. But for water and some certain liquids, we say freezing. Alright? So this is basically what change of states is all about. I want to believe we have been following it so far. If you have been following my explanation so far, I want you to indicate in the chart that you are following. If you are following so far, if you comprehend what I meant by change of states, please indicate in the comments. Indicate in the comments that you are following. I want to see how many of us are following. All right, I can see your message with me. All right, following. Okay, so do not forget this. Like I mentioned, there's one part that usually is very, it's a jam area of concentration. Let me just bring your attention to it. All right. Now, remember I mentioned earlier that solidification is a general name for when a liquid changes into a solidification. But for certain substances, certain liquids like water, we use the word freezing. All right. So you may ask a question that involves water, and they will tell you that the process where water changes from liquid to ice, from liquid water to ice, is called what? Okay. For such a question, freezing every day, morning, afternoon, night, is your answer. All right. So take note of that detail. Take note of that information. All right. Let me quickly recap change of state so far. I said that whenever it is applied to a body, there are certain effects that it has on such bodies. One of them is change in temperature. It will always cause a change in temperature. Secondly is chemical change like in burning of wood. All right, it causes a change in the chemical properties or the chemical composition of such a substance. Then the third one, we saw physical change. When it is applied to a body, it tends to cause an amount of deformation, which may change how that particular substance is appearing. All right. Then the fourth one, we look at change of state, which we are currently talking about. Then the fifth, and we have so many other ones: thermal expansion, thermionic emission, as the case may be. All right. So that change of state is a substance changing from one form to the other when it is applied at a constant temperature. Okay, so all of this is what entails change of state. So we'll proceed to talk about this change of state. If it is what is responsible for it, I'm expecting that when it is applied to a body, it should result, all right, it should result in the increase in temperature. Then why is the temperature not increasing and this particular substance is changing state? Because it is applied. Why is this heat not causing a change in temperature? Okay, that heat is called the latent heat. All right, so that's what I'm going to be talking about shortly. All right, so let's continue. Let's look at latent heat. Okay, so the issue here now is if it generally results in change in temperature, if it generally results in change in temperature of a body, why does change of state that requires heat, change of state that requires heat for it to happen, right? Why is it that it takes place at a constant temperature? Why is it that the temperature of the body does not increase when that change of state is taking place? That's the question, all right? That's why we have latent heat, all right? So when we hear the word latent, all right, latent simply means hidden. Idios, all right? It means what? Hidden. It's an hidden heat, or should I put better? How am I gonna put it now? It's an unobservable amount of heat. Okay, all right. Now, why is it called hidden heat? For the fact that heat is supposed to result in change in temperature, but this particular heat does not result in change in temperature. That's why it's called what? Hidden. Now, let's see the science behind it. So I'm going to draw a substance, and we are going to visualize the particles that make up that particular substance, or the molecules that are present in that particular substance. For example, let's make use of a solid substance. All right, we are told that the molecules or the particles that make up a solid substance, they are closely packed, right? They are closely what? They are closely packed. Alright? Now, as we can see here, let me try and bring them closer. Alright? Let me try and bring them closer. Alright, so as you can see, these ones up here, they are quite close to themselves. Alright, so when heat is applied to such a body, at the process all the time where the body is about to change from one state to another, this is what happens. The intermolecular bonds that exist between neighboring molecules is broken. It means that the bond that binds two molecules together or two particles of that particular substance together, that bond is broken. Alright? It means that if they were closely packed before, if they are bonded together very close to themselves, and that bond is broken, they will move away from themselves. They will be separated from themselves. It means that their degree of movement will be increased. Their degree of movement will be increased rather. Alright? They will not be seen to just vibrate about their mean position anymore. Because why? The reason for their moving about a mean position, that force, that effect has been broken by a particular amount of heat. Alright? So that heat that is responsible for breaking the bonds between two molecules, okay, without causing a change in their temperature is what is called the latent heat. Alright? So latent heat only breaks bonds. Latent heat only breaks what? Only breaks bonds. It does not cause increase in heat in temperature. It only breaks the bond between molecules of a substance. Solid substance, it will break that energy, that bond that exists between two molecules in that particular solid substance will be broken. And since that bond is broken, the two substances or the two molecules will be seen to move apart from each other. And the more they move apart from each other, the more they move towards the liquid state. Just like the molecules of liquids. They are further apart compared to the molecules of solid. Alright? So if the two molecules start to move away from each other, they will start to resemble the properties of molecules of a liquid, that they are further apart and their kinetic energy is greater than those of what? Solid molecules. They are free to move, they are free to flow, just like the molecules of liquids. Alright? So that bond has been broken. We cause them to move apart from each other. And as they move apart from each other, they transit into the liquid state. Alright? So latent heat only breaks bond. It does not cause increase in temperature. It only breaks bond. That breaking of bond results in a change of state. Alright? So latent heat is a major discuss this evening, because it is what is responsible for change of state. So, in one sentence, what is latent heat? So that latent heat is the amount of heat energy. Latent heat is the amount of heat energy that is required. Is the amount of heat energy that is required to change a substance. From one state, to change a substance from one state to another. To change a substance from one state to another without a change in its temperature. Without a change in its temperature. Alright? So from state 1 to state 2 at constant temperature. From state 1 to state 2 at constant temperature. The heat energy required to change a substance from one state to another state at a constant temperature is called latent heat. Okay, so that's what latent heat is. basically. All right. Now, remember I said that the substance is changed from one state to another. I did not specify what state. I did not specify what state. All right. So if I consider the states that the body is moving from and the states that the body is moving towards, all right, that means that latent heat, we have two major categories. Okay, so we have two major types that can be classified under two. Okay, we have the latent heat of fusion. We have the latent heat of fusion, or we have the latent heat. Oh, sorry, this will be latent heat of fusion, then latent heat of vaporization. Latent heat of fusion and latent heat of vaporization, the two classes of latent heat. All right. Now, remember, I said latent heat causes change of state in a substance at constant temperature. Now, if I'm considering the latent heat of fusion, I mean that particular amount of heat that causes a body to change from its solid state to its liquid state. All right. I am more specific now. What kind of change took place and from what state to what state? From solid to liquid is called fusion. The heat responsible is called latent heat. Okay, changing from solid to liquid is called fusion. The heat responsible for changing solid to liquid at constant temperature is latent heat of fusion. That's the first class. Then the second class is the heat that is responsible for changing a substance from its liquid state to its vapor or gaseous state. All right? The heat responsible for changing a substance from its liquid state to its gaseous state. All right? The process from liquid to gaseous state is called vaporization. Hence, the heat responsible for vaporization is called the latent heat of what? Vaporization. All right? So these are the two major classes of latent heat. All right, that heat that causes change of state in a body without a change in the temperature of the body, latent heat. For bodies moving from solid to liquid, latent heat of fusion. For bodies moving from liquid to vapor state or gaseous state, latent heat of vaporization. I want to believe this is clear so far, clear as ABC and 1, 2, 3. All right. So if you have any question as per what I've said concerning latent heat being an hidden amount of heat, all right, and hidden amount of heat, what I would usually call a silent worker. All right. You do not necessarily see its effect in terms of change in temperature, but it is causing a change in state. All right. It's called the hidden worker, the silent worker. It works behind the scene. It does not like showing itself. Understand? It's a smooth worker. It works, but does its thing and then it goes off. All right. It's called the hidden amount of latent heat. Causes change of state without observable changes in temperature. All right. So that is latent heat of fusion and latent heat of what? Vaporization. All right. So picture boiling water. Picture any kind of substance that can melt, or any kind of substance that can change from liquid to vapor. Okay, this amount of heat is always present. This amount of heat is always present. Okay, so now, like you all know, I'll try to be very slow here. We're about entering the calculation aspect. Like you all know, in physics or in science in general, we believe in concepts and theory, but most times we also believe in quantification, measurement. Can this particular quantity be measured, and how can it be measured? All right, let me digress a little bit. We've always heard about the Newton's laws of motion. All right, if you consider the Newton's first law of motion, it was just Newton's efforts to show to us that force is what is responsible for movement. Force is what is responsible for motion. Force is what is responsible for acceleration, for the motion of a body. Force is what is responsible for breaking the inertia of a body, for breaking that state of rest or uniform motion of a body. That force is responsible for it. Okay, but that law did not really give us much information to how that force can be measured. That's why he had to bring in a second force to explain the amount of acceleration, the amount of motion that force can supply to a body. That's why we saw the second law of motion. All right. So bring that back to latent heat. We cannot just talk about latent heat without putting out something out there on how we can measure or quantify latent heat. How we can quantify latent what? Latent heat. All right. So let's see our definition for latent heat. Oh, okay. So we are going to be seeing this definition under 2. We'll first of all look at it under latent heat of fusion. Latent heat of fusion. Latent heat of fusion. All right. I said earlier that latent heat of fusion is the amount of heat required to change a substance from its solid state to its liquid state at constant temperature. All right. That's the definition for latent heat of fusion. And latent heat of fusion, allow me call this HF, is giving us the product of the mass of the substance, times, let me use LF, okay, times LF. All right. This is the mass of the substance. LF here is standing as the specific latent heat of fusion. Yes, we have introduced another quantity now. All right. The latent heat of fusion is equal to the product of the substance mass times the specific latent heat of fusion of that substance. Okay, not to forget, in our previous class, if you haven't watched it yet, I would advise that you go back to our previous live classes, all right, and see or hear what we talked about specific heat capacity. All right. So this case, this LF is standing as a specific latent heat of fusion. Specific latent heat of fusion. That's what LF is standing for. Specific. Okay. I'm going to emphasize this word, specific. Okay. Let us consider a situation where we have 5 grams of a body. We have 5 grams. So let me use kilograms. We have 5 kilograms of a body that is 5 kilograms. Okay. When I speak about specific, I'm trying to consider each gram that makes up this 5 kilograms. Sorry, each kilogram that makes up this 5 kilograms. I'm talking about 1 kilogram, 1 kilogram, 1 kilogram. Okay. 1 kilogram, that's on that 1 kilogram, right? So it took 1 kilograms to make 5 kilograms, right? Okay, so it means that if I'm considering the heat that is required to convert 5 kilograms of a substance from one state to another, and I call that latent heat of fusion. All right. If I am being specific, I'm going to now talk about if this for the whole 5, if latent heat of fusion is for the whole 5 kilograms, what about the latent heat that is responsible for just 1 kilogram of that substance that is being changed from one state to another? What if I consider just 1 kilogram of that particular ice that is being melted from ice to liquid? I want to consider just 1 kilogram of that 5 kilogram ice. What latent heat is responsible? The latent heat responsible is what is called the specific latent heat of fusion. Specific latent heat of what? Fusion. This is the heat responsible to change 1 kilogram of a substance from its solid state to its liquid state at constant temperature. That is my LF. But do not forget that my HF is latent heat of fusion, the heat required to change a substance from its solid state to a what is liquid state. LF is the amount of heat required to change 1 kilogram of a substance from its solid state to its liquid state at constant temperature. That means HF for latent heat of fusion is equal to M LF. This will form our first equation for today. M LF. HF, latent heat of fusion. M, the mass of the substance. LF, the specific latent heat of fusion. Now, if you observe, I did not mention anything as temperature change here. Why? Because change of state takes place at a constant temperature. Alright? So this is the first thing that we must take note of. Alright? So from my equation 1, I can say that the specific latent heat of fusion is latent heat of fusion over the mass of the substance. Specific latent heat of fusion is equal to the latent heat of fusion divided by the mass of the substance. Okay? What is the SI unit for specific latent heat of fusion? Latent heat of fusion is measured in joules. Everything heat is measured in joules. Latent heat of fusion is measured in joules, right? While mass is measured in kilograms. Okay? So my specific latent heat of fusion is measured in joules per kilogram. In joules per kilogram. My specific latent heat of fusion is measured in joules per kilogram. Latent heat of fusion is measured in joules, but specific latent heat of fusion is measured in joules per kilogram. Alright? So take note of this also. Okay? So if you are following the code, let me see you drop a message that you have been following so far. Let me see you drop a message that you have been following so far. If you have been following. If you have been following, let me see you drop a message. Sir, I've been following, sir. You have been following, drop a message that you have been following. Okay, that's one. That's one. All right, so we'll quickly see a question. Or should we finish up first? Okay, let us finish up with latent heat of vaporization. Then we'll see questions under it, and then we'll tie it back again to questions involving change of state generally when we talk about ice melting to steam. Okay, so it means that ice transits two states. Ice went to liquid, and then from liquid to steam or to vapor. We're going to have questions under that also. That is where most students encounter certain challenges. Okay, when we are told that a substance changes from steam at a particular from ice at a particular temperature to steam at a particular temperature. Students usually get confused with such questions. We are going to address them in this live class. We are going to address them in this live class. All right. So I would want you not to get distracted. I want you not to get distracted. Please try and stay in class. Try and stay in class. Break off any form of distractions. Break it off and try and be present as much as possible. How I wish some persons can actually be on this call. I observed that from the classroom, from the WhatsApp class, most of them are not here. It's all good. All right, we'll still do well to proceed. For as many of us who are on the call and who have been active, you will see results soon, like very soon. All right, so we'll continue right about now. We'll look at latent heat of vaporization. Okay, so let's see. Latent heat of vaporization. Latent heat of vaporization. So we have seen for latent heat of fusion. Now we want to consider latent heat of vaporization. Okay, what really happens when a particular substance is transiting from its liquid state to its vapor or gaseous state? How do we quantify that amount of heat? How do we measure that amount of heat that is responsible for changing, for example, for changing liquid water to steam or vapor? All right, what really happens and how do we quantify it? So first of all, what is latent heat of vaporization? What is latent heat of vaporization? Latent heat of vaporization is the amount of heat energy that is required to change a substance. Same, almost similar definitions, just some key points, some keynotes. All right, is the amount of heat energy required to change a substance from its liquid state. To change a substance from its liquid state so its gaseous state at constant temperature. Once again, at constant temperature. It must be specified at constant temperature or without the temperature changing or with the temperature remaining the same. Okay, with the temperature remaining the same at constant temperature or without the temperature changing. Okay, so let's picture water, for example. I'm going to use the symbol H2, the chemical symbol H2. When water, for example, is changing states from its liquid form to its gaseous state, it does so at a particular constant temperature. It does so at a particular constant temperature. Water in its gaseous state is called steam. Why? I'll call this one liquid. Okay, I'll call this one liquid. All right. The process where water transits from its liquid state to steam, so that process is called vaporization. Okay, and this vaporization takes place at a constant temperature, the temperature of 100 degrees Celsius. It's a constant and a definite temperature for pure water. All right, for pure water, vaporization or change in state from liquid to vapor takes place at 100 degrees Celsius. It's a constant value for pure water. All right, it's a constant value for pure water. It's at that temperature that water changes from liquid to what? To steam. Changes from liquid to steam. All right. So the heat responsible for this is known as latent heat of vaporization. I'm going to represent it as HV, latent heat of vaporization, HV, and it is given as the mass of the liquid substance being changed into its gaseous form times LV. Remember the first one was LF, standing for specific latent heat of fusion. This one is LV, standing for specific latent heat of vaporization. So HV here is latent heat of vaporization. Latent heat of vaporization. M is the mass of substance. Okay, the mass of substance, and LV here is the specific. LV here is the specific latent heat. Specific latent heat of vaporization. Just like we saw earlier, all right? This specific is talking about 1 kilogram of the liquid. The heat energy that is required to convert 1 kilogram of the liquid from liquid to vapor. All right, it's called the specific. Just one. While latent heat of vaporization is talking about the whole mass of that liquid. But this one is just specific. Give me one, just one. Let me consider in detail, in a microscopic level. I want to see the amount of heat that is responsible for changing that particular substance from its liquid state to its vapor state. All right, so it is giving us this. Now, every form of heat, like we have the latent heat of vaporization, is measured in joules. Okay, LV, just like LF, if I make LV the subject formula here, is going to be LV equals HV over M. So what would be the SI unit, the standard unit of measurement of specific latent heat of vaporization? All right, same thing. Latent heat of vaporization is given in joules, right? Over the mass of the substance is given in kilograms. So once again, LV and LF has the same SI unit, joules per kilogram. The specific latent heat of vaporization is the same as the specific latent heat of fusion, and it is given as joules per kilogram for when a substance is changing from its liquid state to its what? To its vapor state. Okay, so this is just all that there is to latent heat of vaporization. This is all that there is to latent heat of vaporization. Okay, so we'll be seeing calculations soon. Before we end our class, we'll look about 3 to 4 calculations where I'm going to be explaining in details different forms, different ways an examiner can bring questions under this particular body of physics, how they can present it, what angle can they come from. All right, but because you are in this class, you will not be caught off guard. You will not be caught off guard. Yes, all right, because we are going to be exploring those ways. But before we do that, let me quickly bring your attention to something that usually helped me while I was in school to understand calculations under latent heat very much. All right, I'm going to show you. It's called the heat line. I usually call it the heat line. Okay, I call it the heat line. I know you know number line in mathematics. Okay, this one I call this one the heat line. This is my heat line. What does the heat line helps me to do? All right, if I'm given a question under this particular topic and I'm told that ice at a particular temperature, let's say I'm giving ice at a temperature of minus 10 degrees Celsius. All right, if ice at minus 10 degrees Celsius is melted completely, or or changes, ice at minus 10 degrees Celsius changes completely into steam, calculate the total amount of heat energy required. Calculate the total amount of heat energy responsible for changing ice at minus 10 degrees Celsius to steam at 100 degrees Celsius. That's where you will need my what? My heat line. All right. So let's see. If I'm considering ice at minus 10 degrees Celsius was taken to steam at 100 degrees Celsius. How does my heat line help me? Now watch. Now if I'm adding heat to a body, the temperature will increase from the left to the right. Okay? The left and here's the right. On the application of heat, the temperature of the body moves from the left to the what? To the right in an ascending order. It means from a lower, smaller value to a higher value of temperature when it is applied. Okay? But when the heat flow is from the right to the left, it means that heat is removed from that body. That will cause the temperature to move from a higher value down to a lower value. Okay? From this simple question I just mentioned, we are considering ice at minus 10 degrees Celsius that was changed completely to steam at 100 degrees Celsius. What does that mean? It means that it was applied, so therefore I'm expecting an increase in the temperature. It was applied, so I am expecting an increase in the temperature. It means that I'm moving from the left to the right. Now let's see how that goes. I have ice minus 10 degrees Celsius. Ice at minus 10 degrees Celsius. It means that the ice is currently way below its melting point temperature. What is the melting point temperature of, let's say, ice when I'm considering water? The melting point temperature is 0 degrees Celsius. Alright, so it means it's at this 0 degrees Celsius that ice will start to melt. For every temperature below it, it cannot melt. Alright, so for me to make this ice at minus 10 degrees Celsius to melt, I must first of all apply heat that will bring it to 0 degrees Celsius. Understand? So it can only melt at 0 degrees Celsius. Then now the ice is at minus 10 degrees Celsius. Before it will start to melt, I will have to raise this minus 10 back to 0. Mind you, minus 10 is lesser than 0. Mathematics students, take note of that. 0 is a greater value than minus 10. Alright, so I must first of all apply heat that will take the temperature of the body from minus 10 to 0 degrees Celsius. Alright, so in that case, I will have an amount of heat. I must supply it an amount of heat. Alright, remember our previous topic on heat measurement. I must supply it an amount of heat energy, H. Okay, it must gain an amount of heat energy. Let me call that H1. Okay, this is not the heat that will cause it to melt. So this heat is just to raise the temperature from minus 10 to 0. Raise the temperature of the ice from minus 10 to 0 degrees Celsius. Okay, now it is at this 0 degrees Celsius that the ice will start to melt. It is at this 0 degrees Celsius that the ice will start to melt. Okay, so what heat energy is responsible for melting ice? That's what we saw earlier. We call it HF. Remember, the latent heat of fusion is responsible for the melting of ice. Okay, so after the normal heat has raised the temperature of the ice from minus 10 to 0, another kind of heat, which is the latent of fusion, will cause the ice to melt at that 0 degrees Celsius. It means that the ice will have to melt first at that 0 degrees Celsius at a constant temperature value. Okay, that heat is called the HF. Okay, we are not done yet. Okay, so we have seen that. Now that all at this 0 degrees Celsius, that's when all the ice will turn to liquid, right? Okay, so it means that at this point I'll be having liquid also at 0 degrees Celsius. At this point, I'll be having liquid at 0 degrees Celsius. Okay, now if I apply more heat to that liquid, remember all the ice has been turned or changed into liquid. So it means that temperature can now change. Temperature can now increase. Okay, so from this point to the boiling point of the water, what is the boiling point of pure water? 100 degrees Celsius. Okay, so from 0 degrees Celsius to 100 degrees Celsius, another amount of heat must be applied to raise the temperature of the body from 0 to 100. An amount of heat must be applied. That amount of heat, let me call it H2. An amount of heat must be what? Must be applied. I'll call it what? H2. Remember, I have H1 already. An amount of heat must be applied to raise the temperature from 0 degrees Celsius to 100 degrees Celsius. In between here, there is a change of temperature. In between here, there is a change of temperature. But at this 0 degrees Celsius, where change of state is taking place, there is no change in temperature. All right. So the liquid is now raised to 100 degrees Celsius. Right. That is called the H2. Okay. Now that the liquid is at 100 degrees Celsius, that amount of liquid that is at 100 degrees Celsius must be changed to steam. Remember, okay? It must be changed to what? To steam. Now, let me ask you, the heat that is responsible for changing liquid to steam, what is it called? That heat is called the latent heat of vaporization. It's called the latent heat of what? Vaporization. The latent heat of vaporization. All right? It is at 100 degrees Celsius that a liquid is converted to vapor, right? So it means that at this point, all the liquid must be converted to vapor at 100 degrees Celsius at a constant temperature. All right. So from what I said earlier, for ice at minus 10 degrees Celsius to be raised or to be brought to steam at 100 degrees Celsius, what heat is required? The total heat that is required is equal to H1, which is the heat that raised the ice from minus 10 to 0, plus HF, which is the latent heat of fusion, the heat that caused a change of state, that converted all the ice to liquid, that's HF, at constant temperature of 0 degrees Celsius, plus when all the ice has been melted to liquid, the temperature of the liquid was now raised again, was increased from 0 to 100. The heat responsible for changing the temperature of the liquid from 0 to 100 is H2. Alright? Now that the liquid is at 100 degrees Celsius, at that 100 degrees Celsius is where liquid starts to change to vapor or to steam, right? So what it is responsible for converting liquid to steam or vapor is called a latent heat of vaporization. So put all together, the total heat required in this case is equal to H1 plus HF plus H2 plus HV. All right. So usually JAM or maybe WAEC will usually ask you to calculate the total heat from minus 10 or from any other value below 0 to a particular temperature value in between here, or maybe even after. All right. But if you understand what I just explained now in my heat line, there is no way JAM or WAEC will put the question that will throw you off balance. If you understand the flow of heat in this my heat line, you will not have any form of issue. Now, I believe in your heart you will be asking, sir, this H1 and H2 that you wrote, what is the formula? Do not forget, the heat quantity a body can receive or a body can lose is given as mc delta T from our previous class. Alright, so H1 and H2 takes this form, where m is the mass of the substance, C is the specific heat capacity of that particular substance, then this is the change in temperature. The difference between the final temperature and the what initial temperature. Okay, so this should not be an issue. Okay, so I'll give us time to ask questions. All I've been saying since, if it's not clear to you, do to let me know before we start solving questions. Is there any gray area? Anything I explained just right now that you really did not understand, you did not get? You can ask before we proceed to calculations proper. Before we proceed to calculations proper. Any gray area? Anything I explained that you really did not understand? You can ask now. We're going to see like three questions today, and subsequently during the course of the week, I'll be dropping video lessons on calculations around this particular topic, as it has to do with WAEC and JAM. All right. So, is there any question? If there are no questions, indicate. If you have a question, please ask. Drop it in the live chat. Any question? Any question from the house? Any question from the house? Any question? Any question? If you have a question, please indicate. If you have a question, I'm waiting. If you have a question, ask now. Before we continue, ask please. If you have a question, I'm waiting. This class is for you, not for anybody but you. So if there's an area that is not clear to you, please ask before we proceed. All right. If you are still on the call, let me know. Sorry for the break in transmission. Sorry for the. If you are still in the class, please let me know. Indicate, please. Sorry for the interruption earlier on. If you are still in the class, please let me know that okay. That's a nice one. Thank you. Thank you. We had just a bit of network challenge earlier on. Okay, JC, if I can see you clearly, you said I should repeat the part I said earlier before I talked about the question. All right, so let's see together. Okay, so I was talking about H1, how to quantify H1 and H2. What does H1 and H2 stands for, right? I mentioned that if you have been following previous class, previous live sections where we talk about heat measurement, we mentioned that the heat quantity of a body, the amount of heat a body can possess, depends on the mass of the body, the specific heat capacity of the body, and the temperature change that the body undergoes when that heat is applied. All right. So if I apply an amount of heat that causes the body to move from -10 to 0, okay, so it means that the temperature change is between T2, that's the new temperature, and the initial temperature. All right. So the mass of the ice times the specific heat capacity of ice times the change in temperature, T2 minus T1, that's my H1. Okay. Same thing goes for H2. Same thing also applies for what? For H2. When the liquid is now in the liquid is at 0 degrees Celsius and we want to raise it to 100 degrees Celsius, okay, the heat that is responsible can be measured from this same formula: the mass of the liquid times the specific heat capacity of the liquid times the change in temperature. In this case, the initial temperature is now 0, then the final temperature is now 100. All right. So with my values, I can get the heat quantity that is required to move the body from 0 to 100 and from -10 to 0. Okay, so that's what I was saying earlier on. Okay, we are going to see a question that is related to this right about now. Something like this, I think, almost the same value. Okay, so stay tuned now. I'm going to send that question to the chat. All right, I'm going to drop it now. Send it. All eyes should be on it. Let's just solve this one and one before we call it a day today. All right, so I'm about sending it right over. I'm about sending it now. Okay, sorry, taking a little bit of time. Okay, so let's see. I'll be dropping it now. Oh, too long. Okay. Give me some time, please. Okay. I think my question is quite long. All right, so I'm just going to send the question part, then I'll write out the constant given to us. Okay. Okay, so this is it. This is the question. It says a 0.2 kilogram sample of ice. A 0.2 kilogram sample of ice at -10 degrees Celsius is heated until it becomes steam at 100 degrees Celsius. Is heated until it becomes steam at 100 degrees Celsius. All right, so let's solve just this question. Let's just see just this question. I will try not to clean this part because this my heat line will help us here. Try not to clean this part. Okay. So let's see the solution to that up here. So I'll leave this one aside. Okay. So let's see the solution to this question. Alright, so let's list out all the parameters from that question. Okay, so it says that a 0.2 kilogram sample of ice. Alright, so it means that the mass of ice, M ice, is equal to 0.2 kilogram. Mass of ice is 0.2 kilogram. Okay, like I mentioned in the previous class, whenever you are given a question, before you start building blocks that would obstruct your understanding, all right, do well to list out all the parameters, all the quantities mentioned in that particular question. So mass of ice is 0.2 kilograms. That's one. It says at -10 degrees Celsius. So the initial temperature of the ice was -10 degrees Celsius. All right. Okay. It's heated until it becomes steam. It's heated until it becomes steam at 100 degrees Celsius. All right. So now let's come back to this my heat line. I hope it's clear enough. Let's come back to my heat line. I want to believe it's still clear. You can see it very well. Except for the network disturbing us. I doubt. Can you see it? If you can see it, please let me know. Alright, so the ice was initially at -10 degrees Celsius. For ice to move to steam at 100 degrees Celsius, I mentioned earlier that ice must first of all undergo melting. Now that raise in temperature to 100 before it will now be converted from liquid at 100 degrees Celsius to steam at 100 degrees Celsius, right? So I will have to move from -10 to 0 first, all right? So from T1, I must move to T2, which is 0 degrees Celsius, all right? Then again, after the melting has taken place, I will have to move from 0, which is T2, to 100, which is T3. So my T3 is 100 degrees Celsius. Okay, do not forget that for melting, the temperature is constant. I will not use any change in temperature. For vaporization, temperature is also constant. All right, so these are my temperature values. From -10, the temperature of the ice must be raised to 0. Then at this 0, melting will take place. When I have liquid at 0, that liquid at 0 must then be converted to liquid at 100. Before this constant value of 100, boiling has to take place that will convert the liquid to what? To vapor. Alright? So it's just like this. The heat will be required to change -10 to 0. Alright? Then at 0, heat HF will be required. From 0 to 100, H2 will be required. Alright? From at this 100 point, okay, vaporization will take place at this 100 degrees at a constant what? Value. So the question we are being asked in this particular question is find the total heat energy required. Find the total amount of heat required. Find the total amount of heat required. I think the network is clear from here. Can you see it now? Can you see it now? The network seems clear from this end. Confirm, please. Okay. It's clear from my end. So this. Check your network. It's clear from my end. How about now? Can you see it now? All right. Okay, so let's proceed now. Okay, so like as I was saying earlier, we are told to find the total heat energy that is required to change it from -10 to 100. Okay, so I have written it out before now. The total amount of heat is the H1, that is this first heat, that will change it from -10 to 0. Before HF, we now melt it at 0. Alright? After HF is done, H2, we now raise it from 0 to 100. Okay? When H2 is done, HV, we now change the liquid at 100 to steam at 100. Alright? So we have 4 different heat energy that will give us the total energy. Okay, now what are the constant values here? What are the constant values that we have here? What are the constant values that we have here? All right, so let's see the constant. The constant values that we have for this question, we have the sea ice, that is the specific heat capacity of ice, was given to us as 2,100 joules per kilogram per Kelvin. We have CW, that's specific heat capacity of water. We have as 4,200 joules per kilogram per Kelvin. Then we have the specific latent heat of fusion. Let me call that LF, specific latent heat of fusion of ice, given to us as 3.34 times 10 raised to the power of 5 joules per kilogram, right? We also have the specific latent heat of vaporization as 2.26 times 10 to the power of 6 10 to the power of 6 joules per kilogram. Okay, so given all of these constant values, we want to find the total heat energy. Okay, so how do we go about it? We'll get H1 first. We'll get H1 first. After getting H1, we'll get HF. After getting HF, we'll get H2. Then after H2, we get HV. At the end of the day, we'll add all of them together. Okay, the total energy that 1, 2, 3, 4 will give to us is the heat energy required to change minus 10 degrees Celsius ice to steam at 100 degrees Celsius. All right. For board constraints, please you allow me to clean this off so that you can solve. You allow me to clean this off so that we can solve. Right. So let's go. I'm going to get H1. Do not forget, HT is equals H1 plus HF plus H2 plus HV. Okay, so let's get H1. Remember that H1 is M, right? MC delta T. Do not forget. Alright? H1 is the amount of heat that changes it from minus 10 degrees Celsius to 0 degrees Celsius, right? So H1 will be equal to the mass of ice is 0.2. Mass of ice is 0.2. I want to go to your calculators now. 0.2 times what is the specific heat capacity of ice? Is 2,100. So here is 2,100 times the temperature change. Okay, so for H1, the temperature moved from minus 10 to 0. Minus 10 is the initial, 0 is the final. Alright, so this is going to be, what's the initial here now? The initial is minus 10, the final is 0. Because I'm moving from minus 10 to 0. Alright, so here will be 0 minus 10. So H1 is equal to 0.2 times 2,100 times 10. So my H1 value will be equal to, okay, we have calculators, let's punch together, 0.2 times 2,100 times 10. Okay, that will give us 4,200 joules. So 4,200 joules is the amount of heat required to change the temperature of ice from minus 10 to 0 degrees Celsius. So we have gotten one, H1, we have gotten it. Now let's go get HF. HF is the latent heat of fusion, and it is given as mass of ice times the specific latent heat of fusion. Latent heat of fusion, mass, and specific latent heat of fusion. So HF is equal to, the mass again is 0.2 times our specific latent heat of fusion, which is 3.34 times 10 to the power of 5. So my HF is equal to, let's do that math, 0.2 times 3.34 times 10 raised to the power of 5. 0.2 times, okay, so that will give us 66,800. 6,800. This is the amount of heat that melted the ice at 0 degrees Celsius. The amount of heat that melted the ice to liquid at 0 degrees Celsius, 66,800. Okay, so how many write under here? I hope it's clear enough. Okay, so now I've got HF. I want to get for H2 now. All right, H2 we also take the form MC delta T. But this time around, I'm considering from 0 to 100. All right, so H2 will become the mass of the substance. If ice that is 0.2 melts, it will also become water that is 0.2. So the mass of water here is 0.2 times the specific heat capacity of water. Remember, the ice, as all of them has been turned to liquid water. So I'm considering the specific heat capacity of water. So 0.2 times 4,200. Let's consider our temperature change now from 0 to 100. So initially I am at 0. Finally I got to 100. So it will be my final minus initial. Alright? So my H2 therefore will be equal to 0.2 times 4,200 times 100. So this will give us 84,000 joules. Okay, so 84,000 joules of energy was required. 84,000 joules of energy was required to change the liquid from 0 degrees Celsius to 100 degrees Celsius. So I've gotten my H2. Now, let me get the HV now. Alright? HV is the latent heat of vaporization. And latent heat of vaporization is given as the mass times the specific latent heat of vaporization. So HV is equal to mass again is still 0.2 because the substance remains the same. 0.2 times the specific latent heat of vaporization, that is 2.26 times 10 to the power of 6. So what is my latent heat? My latent heat of vaporization. Okay, so that will give me 2.26 times 10 to the power times 10 to the power 6. 2.26 times 10 to the power 6. That will give us 452,000 joules. Okay, 452,000 joules is required to raise the temperature of the liquid at 100 to steam at 100. Okay, so finally, therefore, my total energy, that is H1, HF plus H2 plus HV, will be equal to 4,200 plus 66,800 plus 84,000 plus 452,000. If I sum all of this up together, let's do the summation of all of this. 4,200 plus 66,800 plus 84,000 plus 452,000. All of this will go to 607,000 joules. Alright, so this is the answer to this particular question. 607,000 joules of energy will be required to raise the temperature of ice at minus 10 degrees Celsius to steam at 100 degrees Celsius. Simple as ABC, solved in details. Solved in details. I want to believe this is clear enough. I want to believe this is clear enough. So just take a while to go through the solution. Take a while to go through the solution. Take a while to go through the solution. Any question as regards the solution on the board? Something doesn't seem clear to you? Ask before. Ask if there's a question that you have also that you want me to provide solution to as regards this topic. You can also drop it. We have 6 minutes away from the end of this class. So there's a question as relating to this solution on the board. One or two things is not clear to you. You can let me know in the chat. You can let me know in the chat. One or two things is not clear to you. You can let me know in the chat. You can let me know in the chat. One or two things not clear to you. Anyone? Anyone? Is this soft solution very clear to everybody? Please indicate. Our time is fast spent. Solution clear enough to everybody? Please indicate. Please indicate. Any problem? Any further question before we call it a day? Okay, at the end of this live, I'll be dropping some questions on the comment section in this live video. I'll be dropping some questions, and I would really love if we can provide solutions to those questions. So when I drop it and you solve is I want to send the solution to the comment section. All right, I'm going to be dropping some questions to the comment section of this live class. After the end of this live section, I want us to provide solution to it and send. All right, and send it on the comment section. Okay, that's one coming in. This is not a question on the okay. 200 grams of ice added to 500 grams of water. Okay, now so what is the final temperature of the mixture, right? So I will solve this one and we'll call it a day. I'll solve this one and we'll call it a day. Okay, so please, one that is on the call, that is on this particular class, should please pay attention to this particular question. Okay, so let's see. Let's solve together. Bring the pin. All right, so let's solve now. So it says, okay, 200 ice at 0 degrees Celsius is added to 500 grams of water at 60 degrees Celsius in an insulated container. Okay, let me just explain here. An insulated container is like a container that does not conduct heat easily. It means that if a content, let's say water is kept in it, the temperature of that water kept in this insulated container will remain the same. Okay, nothing will be lost to the environment. Nothing will be lost or will be brought into the container. No heat will be added to the container. All right, so it is not lost to the environment. Okay, the heat interchange is only between the elements that are present in that system. For example, the ice was dropped in that container. The heat exchange will only be found between the ice and the water that is in the insulated container. So that's the idea. Okay, so let's see the solution, right? So let's go. It says ice, the mass of ice in this particular question is 200 grams. Okay, we must convert this. Okay, so if I convert this mass, I'm going to get 0.2 kilograms. I'm going to get 0.2 what? Kilograms. Sorry for that. Sorry for that. Okay, so the temperature, the initial temperature of this ice, we're told that the ice is at 0 degrees Celsius and is added to 500 grams of water. So mass of water, 500 grams of water, that is 0.5 kilograms divided, okay, that's 0.5 kilograms. Then this mass of water that is 0.5 kilograms, we're told that it was at a temperature of 60 degrees Celsius. 60 degrees Celsius, that's the temperature of the water. 0 degrees Celsius is the temperature of ice. Okay, it means that the ice is already at 0 degrees Celsius. Now it says assuming no heat was lost, what is the final temperature of the mixture? It means that what is CF, final temperature, and constants are given here. Specific latent heat of fusion, that's LF. LF is 3.336 here. Okay, this was given in ordinary form. So here's 336,000. 336,000 joules per kilogram. 336,000 joules per kilogram is our LF. Then our CW, like we know, is 4,200 joules per kilogram per Kelvin. Now, observe this particular system. No heat was lost to the environment, but there was heat interchange between ice and water. The ice was dropped into a container that is already containing the water, and the water is at a higher temperature of 60 degrees Celsius. What do you think will happen to that particular system? The water will lose its heat. Okay, the water will lose some of its heat. The water will lose some of its heat, and that heat that it will lose will be absorbed by the ice. Okay, the heat that the water at 60 degrees Celsius will lose will be gained by the ice, and it will cause the ice to melt. Okay, so heat lost by water equals heat gained by ice. Okay, remember what we said in our last class. So heat lost by water H2 is equal to heat gained by ice. Okay, the heat gained by the ice will cause the ice to melt. So I am considering latent heat of fusion. Then heat lost by water is my normal heat that we know before our previous class. What is that heat? That heat is given as mass of water, specific heat capacity of water, then times the temperature change that water will undergo. Water was first of all at 60 degrees Celsius. If that water is losing heat, it means that I'm going to place the initial temperature of that water, T2. I'm going to place T2 first minus the final temperature that the water will be after losing heat. Do I know the temperature? No. Alright? I do not know the temperature of the water. So that's my final temperature. And it will be equal to the heat gained by ice. Alright? It will be equal to the heat gained by ice. What is that heat gained by ice? The heat gained by ice is giving us mass of ice times the specific latent heat of fusion of ice. That will be 336,000. 336 what? 1,000. Alright? So this will be, I think, one more thing. I think something is missing. Something is missing. Heat lost by water, heat gained by ice, and I think something is missing here because I'm coming. The heat lost by water must be equal to the heat gained by ice. Not just that. Heat gained by ice, 0 to Tf. That'll be Tf minus 0. Tf, okay. Alright, okay. Something is missing. The heat supplied to the ice does not only melt the ice, it also causes the ice temperature to increase. Alright, so I must have H2. Alright, HF is this, mass of ice already is 0.2. Let me just leave it as this question. So there will be mass of ice times LF plus this one, the heat loss from here, part of it to be used to melt the ice, then part of it to be used to raise the ice to a particular temperature. Alright, so that will be my H2, which is mass of now water, because ice has melted, so it is now water 2 times specific heat capacity of water times the temperature change. Water at 0 degrees Celsius that is receiving heat, we move from 0 to a higher value, so it will be Tf minus T1. It will be Tf minus what? Minus T1. Okay, so let's see that now. So what's the mass of water? The first water mentioned, that's 0.5. 0.5 times 4,200 times T2 minus Tf. T2 is 60. So it will be 60 minus Tf. I'm looking for Tf, do not forget. Alright? Everything here will be equal to mass of ice is 0.2. That will be 0.2 times 4,000. Sorry, that will be 336,000 plus this other mass. That will be same mass of ice, 0.2 times 4,200. Tf is not known. T1 is 0. So it's like having here as my what? Tf. Okay, so let's break this down further. 0.5 times 4,200, your calculators. 0.5 times 4,200. That'll give me 2,100 into 60 minus Tf equal to 0.2 times 33600. That will give me 67,200 plus 0.2 times 400 times 4,200 rather. That will give me 840 Tf. That will give me 840 watts Tf. Let's open this bracket. If I open that bracket, I'm going to get that 2,100 times 60. That is 12600. 126,000 minus 2,100 Tf equals 67,200 plus 840 Tf. Collecting like terms, I'm going to get minus 2,100 Tf minus 840 Tf equals, okay, it will be 67,200 minus, when I bring this one over, 126,000. 126,000. Oh, space. I'm lost for space. I'm going to manage this side of the board. So that is true. This minus this will be 2,100. That's minus 2,100 minus 840. That'll give me minus 2,940 Tf equal to 67,200 67,200 minus 126,000 will be minus 58,800. Minus here will cancel minus, so my TF will be 58,800 divided by 2,940. So dividing this value by 58,800 divided by 2,940, that will give me 20 degrees Celsius. So the final temperature, when I place that amount of ice at 0 degrees Celsius into 500 grams of water that is at 60 degrees Celsius, the total or the final temperature of that mixture, of that combination, will be 20 degrees Celsius. So we see that the water at 60 degrees Celsius, its temperature was dropped down to 20 degrees Celsius, whereas ice at 0 degrees Celsius, its temperature was raised to liquid at 20 degrees Celsius. So here is the solution to that question dropped. Alright, so it's as easy as it gets if only you follow the basics. If only you follow the basics. Alright, so we'll come to the end of our class today. Change of state and latent heat. And like I said earlier, if you still have questions, I'm going to drop my own questions. I'm going to drop in my own questions in the comment section of this live class. Alright, do well to attempt them to provide solution for them. Okay, well, if you have other questions, you can also drop it in the comment section or in the community on my bio. Okay, you can drop your questions there, and I will provide solutions and also send them there as well. Okay, but before then, I'll be dropping my own questions in the comment section. I want to believe this class has been very helpful, like very helpful. Everything explained here was actually explained to the simplest of forms. But if you still do not understand, you can always reach out to me and ask me questions. Alright? Okay? If it's personal class that you want, I also render that service. Okay? Where we get to interact directly, where we get to have a one-on-one section, a personal directed class. All right, you can also reach me on my WhatsApp line. Okay, you can reach me on my WhatsApp line on 081-2121-6596. If you are not in Nigeria, you can use the code +234-8121216596. Okay, so contact me for your personal class, private directed class. Yeah, I will hold your hands and take you through the concept of physics. All right, don't forget, this is still physics clinic live every Sunday by 4 p.m. It is very helpful for those students who are currently preparing for one exams or the other, be it WAEC, be it JAMB, be it NECO, be it post-UTME, all right? Or you're just a beginner, you just want to master the concept of physics. This section is for you. Keep your notifications on. Subscribe if you have not subscribed. Subscribe to this channel so that you don't get to miss out on anything. All right. During the week, I usually send video lessons, calculations, or instructions around other concepts of physics. You can as well follow, like, and comment on those videos. All right, and do not forget to watch them and share it to somebody who needs them. Okay. And if you are yet to subscribe again, I just want to tell you that subscription is free. You do not have to pay any amount of money at all. Just press the subscribe button and be a part of this community and be a part of this channel. Once again, my name is Paul Amin, the Paul with vitamin, and this is my channel, Physics with Paul Amin. And today is Physics Clinic. All right, so I hope to see you in engaging with this community. I hope to see you engaging with this channel. Until next time, I don't know why I'm being called back to tell you again. Do not forget to drop your questions. All right, do not forget to drop your questions. Yeah, we are pretty much limited by time. Time is a restriction. All right, but learning is not restricted on this channel. Okay, so whatever question you have, drop it under this live section, and you get solutions, you get answers to your questions. Thank you once again for being a part of this channel. God bless you and have a great Sunday. Okay? And a great week ahead also. God bless you.